Good morning. I'm pleased to present our research titled Beyond the Expert, Automating Criteria, Weight Re-Identification in MCDA with Swarm Intelligence. This work is a collaboration between researchers from the University of Szczecin and the West Pomeranian University of Technology. We focus on the integration of swarm intelligence algorithms with multi-criteria decision-making methods for the identification of decision-makers' preferences in the form of evaluation criteria weights, based on historical datasets evaluated by experts previously. This research presents proof of concept that is planned to be tested on real-life problems in future work directions. The proposed approach addresses limitations in classic multi-criteria decision analysis models, namely dependence on the knowledge of domain experts used for assigning the criteria weights significance. In this paper, we propose integrating stochastic algorithms based on swarm intelligence, specifically particle swarm optimization and cat swarm optimization, with the multi-criteria decision analysis TOPSIS method. This approach is particularly useful when there is a dataset analogous to the one being evaluated, alongside the results of previous evaluations conducted by experts using a specific multi-criteria method. However, a limitation of this approach is that the significance values assigned to the criteria by the experts which we aim to use in evaluating the current problem are not known. Therefore, stochastic algorithms can be employed to identify the decision-maker's preferences for weights, ultimately enhancing the results by incorporating the identified preferences of the experts. The research presented in this paper aimed to investigate the effectiveness of two selected stochastic algorithms, particle swarm optimization and cat swarm optimization, in identifying the decision-maker's preferences for criteria weights. To achieve this, a two-dimensional decision matrix considering 30 alternatives regarding 9 criteria was filled with random values that ranged from 1 to 100. Reference weights were established using the critic objective weighting method. The matrix was then evaluated with these reference weights through the TOPSIS method, which resulted in scores and reference rankings. In the next step, 100 iterations of the particle swarm optimization and cat swarm optimization algorithms were carried out in order to determine such criteria weights that the ranking obtained using the TOPSIS method and the determined weights would best match the reference ranking. The Euclidean distance between the compared rankings was adopted as the fitness function to evaluate the level of fit, with the goal of minimizing this function's value. In the following step, we verified the results by comparing the criteria, weights, and rankings derived from the particle swarm optimization and cat swarm optimization algorithms with reference weights and ranking. We assessed the convergence of these results to the reference values using correlation measures, specifically the Pearson correlation coefficient for weights and the weighted Spearman correlation coefficient for rankings. The TOPSIS method is based on a logical framework that involves reference points, a positive ideal solution, and a negative ideal solution. Particle swarm optimization involves a swarm of particles, with each particle representing a candidate solution. The particle swarm searches the space in given dimensions and finds the best solution that optimizes the problem. Particle swarm optimization has only 3 controlling parameters, namely the inertia weight, cognition learning rate, and social learning rate. Cat swarm optimization is a swarm intelligence algorithm that was inspired by observing the behavior of cats. The algorithm is designed to model cat behavior in order to solve optimization problems. Each cat operates using two behavioral submodels, seeking mode and tracing mode. The seeking mode simulates a cat at rest, looking for its next position to move to, while the tracing mode represents a cat actively following a target. At the end of the iteration, the final solution is determined by the best position of one of the cats. Let's see some results. The displayed figure shows a comparison of the reference values of the criteria weights and those determined using the particle swarm optimization and cat swarm optimization stochastic algorithms. It can be seen that the most convergent values of the weights determined using the particle swarm optimization algorithm with the reference values were obtained for criteria C1, C4, and C5. On the other hand, the most consistent values of the weights determined using the cat swarm optimization algorithm with the reference values were obtained for criteria C2, C3, C6, C7, C8, and C9. The results indicate that the cat swarm optimization algorithm effectively determined weights that converge more accurately to their actual values compared to the PSO algorithm. This is evidenced by Pearson's correlation coefficient, which is 0.9339 when comparing the reference weights to those determined by the cat swarm optimization algorithm. In contrast, the Pearson's correlation coefficient for the comparison of reference weights with those determined by the particle swarm optimization algorithm is significantly lower, at only 0.6954. This figure illustrates how the fitness function, which measures the Euclidean distance between the reference rankings and the obtained rankings using the criteria weights determined by the particle swarm optimization and cat swarm optimization algorithms, changed over successive iterations of the compared algorithms. A significant decrease in the fitness function value was observed by the fifth iteration of the cat swarm optimization algorithm. In contrast, the particle swarm optimization algorithm showed a significant decrease in fitness value later in the 11th iteration. In the subsequent iterations, the fitness value continued to decrease for both algorithms. The fitness function value stabilized for the algorithm by the 35th iteration. In contrast, the cat swarm optimization algorithm continued to show a decrease in the fitness function value, reaching its lowest point after 92 iterations. The fitness function value achieved with the cat swarm optimization algorithm after all 100 iterations was lower than that of the particle swarm optimization algorithm. This indicates a better matching of the weights determined using the cat swarm optimization algorithm. The rankings based on the weights obtained from the cat swarm optimization algorithm demonstrated a stronger correlation with the reference ranking than those derived from the particle swarm optimization algorithm. This higher correlation of the TOPSIS ranking using the cat swarm optimization derived weights was confirmed by measuring the weighted Spearman correlation coefficient, which is 0.9986. In contrast, the correlation value between the reference ranking and the ranking generated with the particle swarm optimization derived weights is slightly lower, at 0.9965. The differences between the rankings generated by the cat swarm optimization and particle swarm optimization algorithms when compared to the reference ranking are slight. This proves the effectiveness of both stochastic algorithms in determining decision-makers' preferences for criteria weights. Notably, the cat swarm optimization algorithm has been identified as the more accurate. It is also worth mentioning that both cat swarm optimization and particle swarm optimization successfully identified the top-ranked leader, denoted by the symbol A19. The results of the study showed that the considered cat swarm optimization and particle swarm optimization stochastic algorithms can be useful in solving the preference identification problem. This capability contributes to the automation and extends the multi-criteria models with knowledge identified from previously collected data. The proposed approach provides an accurate solution to the problem of re-identifying preferences without relying on direct contributions from domain experts in decision support systems. The investigation reveals that the cat swarm optimization algorithm offers a more precise approximation of results compared to the particle swarm optimization algorithm considered in this work. Future work should focus on comparing the effectiveness of the investigated stochastic algorithms with various values of parameters, as these can significantly impact the final outcomes. Additionally, a comparative analysis incorporating a broader range of stochastic optimization methods would be valuable. Moreover, further research should be extended to include more simulations to check the repeatability and robustness of the results. In addition, it is important to take up the challenges raised by uncertain data represented by fuzzy sets. Finally, the proposed approach should be tested against real-world problems for a more comprehensive evaluation. This work was supported by the Polish National Science Centre and the Ministry of Science. Thank you for your attention.